Alright folks, before we get to the examples on your practice, it's going to be important today that we understand how to factor to solve quadratic equations. So you can grab a piece of scratch paper and go through these here with me. First up, we're going to look at all of these equations here, and you'll notice they're all equal to 0. Step 1 to factoring, as always, make sure your equation is equal to 0. Step 2, we want to look for a GCF. So on this first problem, between 4x squared and negative 9, there's nothing in common, not a number, not a variable, so no GCF. Then, after that, we can go look for our factoring patterns that you learned about in algebra. So when you see two terms, GCF and difference of squares are the only options that you're familiar with. So we're going to look for those here. And you'll notice on this first one, both of those terms are perfect squares. 2 squared and x squared, and then 3 squared is 9. And I want to remind you of the factoring pattern here. If you have a difference of squares, should see minus, and we factor into a times a gets us to a squared. B times b gets us to b squared, but in order for this to be negative, one has to be positive, one has to be negative. The reason we only see 2 terms instead of 3 is because these are conjugates, meaning our middle terms will cancel out. So with that in mind, we are thinking what squared gives us 4x squared, and that would be 2x times 2x. Just taking the square root of what you see. Same thing goes for the second part. 3 is the square root of 9. And then we'll just need a plus and a minus. The zero product property tells us that the first piece of this equation could be equal to 0, or the second piece of the equation could be equal to 0. That's the only way we can multiply to get 0. So what we're going to do here is just set each piece separately. And the first one, if you're trying to get x by itself, we would subtract 3, so negative 3, then divide by 2. Second piece, we would add the 3 over, so positive 3 divided by 2. And those are our two answers. Second one, already equal to 0, so we're just looking for a GCF. Okay, I told you factors can be numbers or variables. In this case, our GCF is a variable. We want to take out that x, and then we're left with x minus 8 equals 0. Still have two answers here. So I've got x equals, the first one says x equals 0, nothing to move, it's just 0. Second piece, we've got to add the 8 over so it becomes a positive 8. Right. The next one, we've got easy factoring. So 2 sets. What makes it easy factoring is there wasn't a GCF and then the a value is 1. Why that's easier is because the only way to get x squared splitting it up would be x times x. So we only have to work hard on the second part. We're thinking of the factors of negative 35 that would combine to be negative 2. So the way I like to do it is thinking about negative means I know I have one positive and one negative. That's the only way it works. So I'm going to start with a plus or minus here. And that way I'm only looking at the numbers I need, not necessarily the signs I need, since they're already plopped in there to start with. So then if we think about the factors of 35, you've got 1 and 35, and you've got 5 and 7. Because this was a negative, we're really looking for a difference of 2, and 5 and 7 have a difference of 2. And how you subtract them tells you which one gets the positive and which one gets a negative. We need this to be a negative 2, so 5 minus 7 would give us that. So positive 5 minus 7, and there's my factored form. You can always check yourself. I encourage you to just do that foiling back. X times x is x squared, that's good. Minus 7 plus 5, that's what we were just talking about. And positive 5 times a negative 7 is negative 35. So solving again, moving the 5 over is negative 5, adding the 7 over positive, two answers once again. On the last ones, we've got some equal to 0 happening, but no GCF means this is our frowny face factoring. So we're going to take our 3 times 8 as 24 to decide what will go in our factored form. So we can't say x times x is 3x squared. That's what makes this the frowny face. It's not automatic. We can plop in here. If you remember the process from Algebra 2 with factoring by grouping, you can go ahead and take care of that. I'm going to show you a different way to factor with the a value not equal to 1. We're talking about still the factors of 24 have to be both positive or both negative, since we are multiplying to be a positive. And because this is a minus, I know they both have to be negative here. But what I'm going to do is talk about how to write this out dealing with both that a value and our factors at the same time. Still the same process for the 14. I want to get to be 14. Since it's a positive number here, I need to add to be 14. So the numbers that work are 2 and 12. Already decided they're both going to be negative. But the problem here is I couldn't go and say x minus 2 and x minus 12 because that doesn't make this first term work. The easiest way to fix that is if the a value is the problem, we're just going to get rid of the a value, dividing that off. But then we have fractions here, meaning we should have fractions here as well. We would multiply to be the 8/3 and add to be the 14/3. All you have to do is match that divided by 3, and you can see that happening. On the top, that's 24 over 3, okay, or 24 over 9, sorry, which reduces to your 8 over 3. Okay, and then same thing here. We're going to add them together, 14 over 3. We keep the denominator. It works. So our job is to make this into factored form the way we're used to seeing it. That means no fractions are allowed. To get rid of a fraction, you just multiply that denominator through. So this is 3x minus 2. Over here, 12 over 3 reduces. So this is just x minus 4. And now you can see by putting that denominator into the front, we actually match up with the original before we divide it by 3. 3x times x is 3x squared. Minus 12 minus 2 gets you the negative 14, and positive 8 to finish. So x equals 2/3 for the first one, positive 4 for the second one. Showing you that process again here. 2 times negative 3 is negative 6. The factors that I need here, because it's a negative, we have to have one positive and one negative. So with that in mind, we're looking for a difference. 6 minus 1 gives us 5. And I want to say minus 1, so I put that there. I'm going to go ahead and divide this 2 on all my pieces, including my factors. That way I can jump right to the answer when I go write my work here. 6 over 2 is just 3, so x plus 3 goes here. And what I showed you here is this denominator just goes in the front. That's the whole idea of getting rid of it. So this 2 would start first, and then I would know x minus 1 from over here. With that pattern, checking it, x times 2x is 2x squared. Minus 1x plus 6x gives us our 5x, and negative 3 to end with. Okay, so just another way to factor using frowny face. Your choice though. You can always go back to your factor by grouping style. X value here is negative 3 for the first one. Adding over and dividing by 2 gives us a positive 1/2 for the second part. We're going to talk today about graphing rational functions. Okay, and so what I want you to do for the first 2 examples, so this is 1 and 2, I want you to pause the video and write down everything you can think about to be true about your graph. Okay, and then we'll come back and chat. First graph first, hopefully you came up with things like the asymptotes that are showing up and the intercepts that are showing up. You could have also talked about maybe domain and range, not as necessary, but definitely we want to know all of the critical features for the graphs. Okay? You may have said that this is a parent function of y equals 1 over x. We have a translation of 1 and 1, that's why our asymptotes moved. Okay? What I want to show you is the equation for this graph. It's called a rational function because you see one fraction in the equation of your function. But this isn't exactly the same if you think about the translation. This graph, if you attempted to write an equation, should have actually been y equals, let me go draw on my asymptote so you can see it more clearly. But right here, where these things intersect, it's a little bit hard to see here, but normally a hyperbola is one diagonal distance here, up one, right one, from where your asymptotes intersect. Okay, ours has been stretched. It goes actually up 3 over 1. So the equation would have looked like 3 over x if I want to go right 1, so it's minus 1. If I want to go up 1, plus 1. This was the equation using transformations of graphs with our parent function. The reason this is equivalent here is to add 1. I'd get a common denominator, and anything over itself is 1. Then you can see the denominator is x minus 1. 3 plus x minus 1 is x. 3 minus 1 is 2. They're equivalent. The reason we like this version is it has a relationship to these two items on the graph. We're going to talk about all of them, but starting with these two. Vertical asymptote ended up staying exactly what it is when we think about translation. It deals with the denominator. It comes from the x value that makes the denominator go to 0 or causes dividing by 0. We know that's a problem. There's a restriction there. The vertical or the x-intercept comes from the point, and we've practiced intercepts so far this year already on a lot of your homework assignments. But remember, an x-intercept is just where y equals 0. If I plug in 0 there, I've got, sorry, my graph did that weird thing. I've got on top x plus 2 and x minus 1. To solve for that, I have to get rid of that denominator. And what's nice about this equation is when I multiply that over, it's times 0, which means just 0 is happening. And that x plus 2 is directly related to the x-intercept because that denominator cancels out. So these two things, you're going to see the opposite of the vertical asymptote in the bottom, and you're going to see the opposite of the x-intercept in the top. All the other items fall into play of the patterns of the graph. So looking here, our horizontal asymptote was at 1. You really don't know a lot about horizontal asymptotes yet, but here's the idea. We're saying we're plugging in x values, and we want to see where the y is headed, or what y values show up. When you have restrictions in the x values that you're allowed to plug in, that usually translate as restrictions in the y value as well. So, keeping in mind our old school way to talk about graphs, I'm just going to make a table of values here to show you why this is ending up looking like 1. So I'm going to pick the x values 1, 10, 100, and 1,000, just to see as x gets bigger. So if I put this on top, 1 plus 2 is 3. And on the bottom, 1 minus 1 is 0. We had the asymptote. We learned about that one, or we saw it in our graph. Second one, 10 plus 2 is 12. 10 minus 1 is 9. This one, 100 plus 2 is 102. And 100 minus 1 is 99. Here, we've got 1,002 and 999. You'll notice these fractions end up getting closer and closer and closer to being the same number on top as you see on the bottom. Meaning, our horizontal asymptote, as you get bigger and bigger, the end behavior is approaching the number 1. And how we can see that in the equation is just recognizing that the top is the equation of a line, x plus 2, and the bottom is an equation of a line, x minus 1. The top is increasing by a rate of 1 or a slope of 1. The bottom is increasing also by a slope of 1. When we take our 1 divided by 1, we get 1. So horizontal asymptotes, if the function on top matches the function on bottom, we just divide the leading coefficients. So on the second graph, we saw a horizontal asymptote of 2, Okay, that's coming from the equation of this graph. And what I want you to do, we'll come back to that. What I want you to do is see if you can do the pattern like we just talked about, just with the vertical asymptote and the x-intercept of writing that equation. Pause the video and see what you can come up with. Remember we said that the denominator was the opposite of this, so that looked like x plus 1. And the numerator was the opposite of this, so x plus 1/2. Well, with this, we never want a fraction inside, so just like we were talking about with our factoring, this 2 is going to move to the front, 2x plus 1, and then x plus 1. We've got a line on top and a line on bottom. Our horizontal asymptote, 2, is right there. Then the only thing we have left to talk about is the y-intercept and where it's coming from. Again, we practiced this on the homework a few times. It takes your equation and plugs in 0. So if I go here and plug in 0 on top, 2 times 0 is 0, plus 1. On the bottom, 0 plus 1. It's just 1 over 1. It ends up being the back half for the constants. But it's just plugging in 0 and simplifying. So, let's take some notes for all of those things. Pause the video and write down these things so we can do the algebra starting with the next example. Alright, here we go. We've got a equation that has a quadratic on top and a quadratic on bottom. This is why we practice factoring. Okay, so let's break this down. Because there's not a GCF, we want the factors of 6 that add to be 7. That's 1 and 6. And then because there's an a value, remember you have to divide that off. First one, 2x plus 1. Second one reduces x plus 3. Always check yourself, because we do a lot of switching signs here. We kept this 1/2 because it built on the factored form. You don't switch the sign until you go to solve things, so coming later. Okay, but you can check yourself just by foiling back. 2x times x gets us that. Outside is 6, inside is 1, that gets us our 7x, and last times last is our 3, so we're good to go there. On the bottom, we just have x squared, so we're starting with x times x, and then factors of 3 are only 3 and 1, both positive since it was a positive 3 and a positive 4 in the middle. So here, hopefully you notice some nice things are happening. Those x plus 3's go away. And I want you to just rewrite what's left. 2x plus 1 was on top, and x plus 1 is on the bottom. Using your notes that you just took, I would like you to pause the video and find the x-intercept, y-intercept, vertical asymptote, and horizontal asymptote. And when you're done, I want you to plot all of those things on a graph. I don't want you to connect any of the points. I just want you to put your vertical and horizontal asymptote as dashed lines, and I want you to plot your points on the graph for me. Pause the video and try that. Alright, remember x-intercept comes from y is 0. So when you plug y is 0, we multiply the denominator over. This becomes 0, and then we just solve for x. So negative 1/2, comma 0. Remember, just opposite of numerator. Y-intercept, you go and put in a 0 here and here. So this says 1 over 1, 0, 1. Vertical asymptote comes from denominator. Negative 1 plus 1 would cause problems, so negative 1. And horizontal asymptote, I like to go back to the original because sometimes factored form can be messy, especially after all this writing. Just divide the front numbers. So y equals 2. So your graph should have looked like an asymptote at negative 1 and an asymptote at 2, and you should have had the points on there, -1/2, 0, and 0, 1. But I told you not to graph it yet because I wanted to talk about one other piece that's missing. These factors that cancel create one other item on the graph that you haven't seen before. This is called a hole. We talked about denominator meaning the vertical asymptote, and the reason that was happening is because we couldn't divide by 0, so whatever number caused dividing by 0, the graph cannot exist. And that looked like a vertical asymptote. But there were two pieces in the original equation after we factored that were in the denominator, which means x equals -1 is a restriction, but x equals -3 is also a problem. It just looks different on the graph. When you see the factors cancel, it's known as a hole. So what I want you to do in your work where you canceled stuff out, I want you to write hole, and then the -3 is the problem, and that's the x value. Grab your calculator for me. You can pause the video if you need to grab it out. But then type in the original equation in your y equals for me. We've got a quadratic on the top and a quadratic on the bottom from the original equation, not the factored one. And you want to put parentheses to say, do the whole numerator group together and the whole denominator group together. That's true for all rational functions if you're graphing them. And then hit a zoom 6. We see this hyperbola shape, and if you trace -1, you'll notice that the y value is blank, and we can see that on the graph as an asymptote. But if you trace -3, you're also going to see y equals 0. But at -3, it looks like your graph has a value. Your calculator is unable to show holes on the graph, just like you don't see the dashed line happening. So there is a hole there, but it can't give us the y value for it. That's our job. Okay, just like we found the y-intercept, if you know the x value, all you have to do is plug it in. So what we're going to do is take the y equals 2x plus 1 over the x plus 1 that we had. You already have this written down. And we're just going to plug in -3. So that's 2 times -3 plus 1 on top, and -3 plus 1 on the bottom. So we get a -6 plus 1 is -5, -3 plus 2 is -2. Our hole has a y value of 5/2. And you can see that on your graph because the curve from your calculator is directly above that y equals 2 asymptote, so it seems reasonable that 2.5 is where it's at. So when you sketch this, going back to my sketch from before, okay, you have all those things on there. What you're going to do is at -3, 2.5, put an open circle and label it. And I'll go ahead and put that asymptote back on so we can see it. And then when you connect this, you'll start at the asymptote, stop right at that hole so you don't cross through it, and then continue on the other side of it. Over here, I'll put these back on. Same thing, we're going to start at the asymptote, go through these points because they're closed, and then end at our asymptote to complete our graph. And now that we have an idea of what we're looking for, graphing these things is going to go pretty quickly if we don't have quadratics. So on example 1, the top and the bottom are not quadratic, which means we skip over the factoring. We just have to use our patterns to come up with the critical points. So this OA we haven't learned about yet. You won't have any of those on your homework. We've got a vertical asymptote though. Remember that comes from the x value that causes problems. The only problems in fractions is if you divide by 0. So we're looking for the number that makes this whole thing 0. That would be -1. Horizontal asymptote comes from the rate of change, or the leading coefficients. Okay, this is a slope of 1 over a slope of 1. When we divide those, because that's what a fraction means, we get y equals 1. X-intercept is just an ordered pair. You've been doing this, you've been practicing. The y is 0. So what you're going to do is go up here and plug y equals 0. I'm just writing down the right-hand side. And we know to solve, when you're given a fraction, you just have to multiply by that on both sides. Right side cancels out, left side goes to 0. 0 equals x plus 2. So numerator is all that's left, so that's negative 2, 0. Y-intercept is also an ordered pair. We've got x equals 0 this time, and I like to just write on top of the original problem. So I'm putting a 0 there, and I'm putting a 0 there. The only thing that's left up on top is 2, and on bottom is 1. 2 divided by 1 is 2. So 0, 2. And then we'll graph it to see the domain. So over to the right, you will need a straight edge. I do care that this is neat, so pause the video if you need to grab out your ID or a ruler. But you're going to start with your x and y axis. You can put arrows on there. I usually don't. It is up to you. Then we're going to go to putting on our asymptotes. Okay, so at -1, if you want to put tick marks, you can. Okay, we're going to dash through. These I would like you to put arrows on and a label. We're going to do the same thing with the horizontal asymptote. That one's at a +1. And labeling it as well. Once you have your asymptotes on your graph, you will plot your points. -2, 0, so to the left 2. Label it. 0, 2 is up 2. And it looks like we have 1 point in each section, which is plenty to draw our curve. You're going to start at the asymptote because we know that's defining our end behavior. Go through the point and end at the other asymptote, our restriction. Doing the same thing on the other side, start at your asymptote, hit the point, and then head towards your other asymptote. Please make sure these graphs have arrows on the end. Domain, starting at that arrow at the left, that's -infinity. And I'm going to stop at my asymptote, that's a restriction in my domain, so I'm stopping at -1, saying it's not included and going past it, so -1 to infinity. Again, because the -1 caused dividing by 0. I would like you to pause the video and try doing the algebra for all of the critical values, the asymptotes and the intercepts, and we can come back together to talk about the graph. You should have gotten x equals -3, y equals -2, an x-intercept of -5/2, and a y-intercept of 0, -5/3. Remember, this is denominator. This one is dividing the fronts. X-intercept is setting numerator equal to 0 because that denominator goes away. You add over the 5 and divide by -2. And y-intercept, dividing the back half because the front goes away. Let's graph it. Starting with your x and y axis, then we're putting on our asymptotes. Again, if it helps you to put tick marks here, 1, 2, 3, go for it. That might help you with your plotting your points. Same thing goes the other direction. There's 1, there's 2. We do have to label both of these. I don't care if it's on the right or left side or the top or the bottom. Just put them near one of the arrows for me. Then we're going to put our negative 5 halves. That's negative 2.5, so left from the origin there, that much, and label it. And then our other one is 1 2/3 down, so a little bit in front of that asymptote. And we're labeling it as well. And it looks like this curve we can take care of. It's got plenty of points. On this side, in theory, we could have a branch up here because of the asymptotes, or a branch down here. Now with us focusing on hyperbolas, we assume it's going to be diagonal here. There's two ways you know that's actually happening. One, we found the x-intercepts and there was exactly one. That means this curve cannot happen. That would indicate it crossed this x-axis again, and that's not possible. We did the math, it didn't happen. There were only one x-intercept, so it has to be down here. Option 2, pick a point and plug it in. The whole idea of shape comes from x values being substituted into this equation. So if you want to know what's happening on the left of negative 3, you just pick an x value that's to the left, like negative 4, and sub it in. That would look like negative 2 times negative 4 minus 5, and on the bottom, negative 4 plus 3. This is 8 minus 5 is 3. On the bottom, you have a negative 1. That tells you at the value negative 4, you should be at negative 3. So very clearly, the graph is happening on this bottom section. Domain then from my graph is negative infinity, stopping at negative 3, union negative 3, positive infinity. Everything but negative 3 works. Alright, number 3, we've got some quadratics here, so we're practicing with factoring once again. On top, we have a difference of squares, so x plus 3 and x minus 3. And on the bottom, we've got x plus 3 and x plus 2. Factors of 6 to add to be 5. And we've got some stuff canceling. So what I want you to do when stuff cancels is remember there's a hole. Go ahead and put it with the vertical asymptote on that same line for me. And the hole is at the x value that makes that 0. So that would be a negative 3. The y value comes from this part of it. Once that stuff's canceled out, we'll just rewrite it. So y equals x minus 3 over x plus 2. This is a nicer equation than the one we started with, so we'll use that to answer questions from now on. Plugging in a negative 3, that would be negative 3 minus 3 on top, and negative 3 plus 2 on the bottom. So that's a negative 6 over a negative 1, which means 6 will be our y value. Vertical asymptote, looking at this, negative 2 causes problem, so x equals negative 2. Horizontal asymptote, y equals, you can use this version or this version, but our coefficients match. And anytime the power matches, then we just have to divide the leading coefficients. Even with quadratics, we're talking about the rate at which they're increasing, and it comes from that coefficient. So we've got a 1 either way. X-intercept and y-intercept. We're just plugging in 0 for y on the first one and 0 for x on the second one. Pause the video and take care of those for me. We should have had 3, 0 for the first one and negative 3 halves for the second one. Just by numerator equal to 0 for that one, and x equal to 0 for the second one. We're going to graph now. Starting with x equals negative 2. Labeled. and then putting on our y equals 1. And then we want to include the whole as one of our important points, not just the intercepts. We just have to make sure that one's open. So at -3, 6, we're putting an open dot and labeling it. At 3, 0, is our x-intercept. And at 0, -1.5 is our y-intercept. And we can see with our asymptotes, this curve is going to start at the asymptote down below and go up to that 1. Here, just don't cross through the hole if you would. At least make sure I know that it's open to finish out your graph. What we haven't talked about yet is domain. When we have a hole and a vertical asymptote, both of those are restrictions in our x values or our domain, so they're going to affect this problem. Essentially, domain cares about denominator, and if there's two things to start out with the denominator, that means you're going to have to stop 2 places. And you just look at your graph from left to right to pay attention to that. So -∞, my first stopping point is this open dot at the x value of -3. I pick up where I left off because it does start right after that. But then I stop almost immediately again at -2. After that, we're used to seeing it, -2 goes to infinity. All right. I'm going to stop there and let you work on your homework. If you do have any questions as you go through there, please come see me. I will give you a warning. When you're talking about quadratics and something doesn't factor, that one, or doesn't cancel, that would indicate that there wasn't a whole. But if there are 2 things in the denominator, that means those 2 things both have to be vertical asymptotes. It is possible to have 2 vertical asymptotes, and you will see that happen on your homework. Good luck.